Lecture 3, Part 1, Mean, Median, and Mode. In this lecture, we'll be looking at measures of central tendency. A measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within the set of data. As such, measures of central tendency are sometimes called measures of location. So the measures of central tendency that we'll be looking at is the mean, median, and mode. In terms of the mean, we'll also be looking at the weighted mean and the geometric mean. Let's start with the mode. The mode is the value of the observations that appear most frequently in the dataset. This is useful in analyzing nominal level data. How do we find the mode? We use a frequency table to find the value that appears most frequently. The problem with the mode is you can have data sets where there are no values that appear more than one time, or you can have data sets where more than one value appears multiple times. So finding the mode. If we're looking at a bar chart, the tallest bar chart would be the mode of that given data set. If we're looking at a data set like this, 639, 66593, the most common observation will be the mode. So in this case, 6 appears 3 times, and therefore this mode is 6. The median. The median of the quantitative data set is the middle number where measurements are arranged in ascending order. How do we follow this process? Well, the first thing we have to do when finding the median is to put your data into ascending order. If the data set is an odd number of observations, then the median is basically at the position of n plus 1, n being the number of observations divided by 2. That'll give us the exact central point of the distribution. However, if we have an even number of observations, we find the median following these three-step process. First, we find the value at n divided by 2, n again being the number of observations in the data set. Second, we find the value at position n plus 1 divided by 2. And finally, we find the average of the two values to get the median. Properties of the median. First, it is not affected by extremely large or small values, and it can be computed for ordinal level data or higher. So you can compute a median for ordinal, interval, and ratio level data, but definitely not for nominal level data. So if we have a data set here like the one seen above, the first thing we would do is put the data in order. And since in this case we have an odd number of observations, the exact number in the middle of the distribution will be the median. And in this case, the median will be 9. Now the mean. The mean of a set of quantitative data is the sum of the measurements divided by the number of measurements contained in the data set, otherwise known as the average. There's two types of means that we'll be looking at. The first type is a population mean based on an observations that were from the entire population of interest. In these cases, the mean is denoted by the value of mu. This is a Greek letter for m, and this denotes the value of the mean. And then you can see that in order to find the mean, you take the sum, this is this symbol here, uppercase sigma, the sum of all the observations, the x's, and we divide it by n, which is the total number of observations in the population. The sample mean is denoted by x bar, and it is found by taking the sum of all of the sample data points and dividing it by the sample size. Mathematically, these are absolutely identical functions. The differentiation between population and sample will become very important when we look at our measures of dispersion. Finding the mean. So here's a simple data set. Here's our numbers, 4, 5, 6, 7, 8. In order to find the mean, the first thing we do is add all of the data points, and when we add this series together, we get 30. The second thing is we divide by the number of observations. In this case, we have 5 observations, so we divide 30 over 5, and therefore the mean of this data set is going to equal 6. Properties of the mean. Every set of interval or ratio level data has a mean. All values are included in calculating the mean. The mean is going to be unique. Now this is a key property here, and we'll be proving this property in the next slide. So the sum of deviations of each value from the mean is 0. So sum of all of the deviations from the mean, so x minus x bars, is equal to 0. What are deviations? A deviation tells us how much each observation deviated from the mean. So observations will have high deviations from the mean, and others will have low deviations from the mean. Let us use the data set to prove the fourth property of the mean. So here's the data set we saw in the previous example, 4, 5, 6, 7, 8. These are our observations, our x values. We found that the mean of this data set is 6. So let's calculate the deviations. So first, let's find the deviation of 4 from 6. So there we take 4, which is our observation, minus the mean, which is 6, and we get -2. So the mean is 2 places above observation number 4. The second observation, 5, is -1 space below the mean. The observation 6 is exactly the mean, so there's no deviation. 7 is 1 above the mean, and 8 is 2 above the mean. So let's sum this up. -2 plus -1 plus 0 plus 1 plus 2. Notice that we get 0, and the property of the mean is proven. Mean versus median. So one very important distinction is to think about how the mean and median are related. In a perfectly symmetrical data set, the mean and the median will have exactly the same value. However, when your data set is going to be skewed, the mean and the median will be different from each other. So here's a little chart that defines the difference between the mean and median. First, in definition, the mean is the average value of the data set. The median is just the central numeric value of the data set. In terms of the extreme scores, which is the important takeaway here, the mean may be affected by extreme scores and will not accurately represent all of the scores. However, the median is not affected by extreme scores. Let's have a look at how, when we think about the mean versus median and how it is going to be shown to us, say, in the media, what differences we would see between showing a descriptive statistic of the mean versus the median. So here's some data on the salary of high school dropouts. Here's our data set, 15,000, 20, 40, 100, and 750. The mean of this data set is $185,000. So you could make a statement such as the average high school dropout makes a mean salary, or makes an average salary, of $185,000. Well, this is extremely misleading because this 750,000 and even this 100,000 is pulling that mean away from the center of the distribution. However, if we use the median, we see a different story, because once we sort the data into ascending order, the median tells us that the average salary is 40,000. Now, one little hint is that the word average can actually be used to describe the mean and the median interchangeably, particularly in newspapers and media. Let's have a look at a real data set. Here we see a representation of the mean household savings versus the median household savings in the United States as of June 2019. Notice here the darker blue, we have the average, the mean. So that's like taking everybody's savings, adding them up, and dividing it by the number of people that in the US. So in this case, we find that the average savings is close to $170,000. However, this may be impacted by people that are very, very wealthy and have very large savings accounts. However, if we purely take every single person, line them up into order, and pick the person exactly in the middle, we'll find that that household saving is only $11,700. So depending on what you want to display in terms of your newspaper and so on, or as a headline, you may say average savings is higher than expected in the United States at over $170,000 a person. Or you may represent it as U.S. household savings is extremely low. The median household savings rate is $11,700. Notice with the same data set, we can tell completely different stories. Now, when to use mean versus median will be a distinction we'll make in a slide or two. How do we detect the skew of a data set by comparing the mean and the median? So when your data is rightward skewed, you notice that this tail is longer on the right side of the distribution. What it's telling us is that there is some extreme large value that is pulling this mean away from the median and it's pulling it over to the right. So in cases where the mean is larger than the median, we have rightward skewness or positively skewed distribution. When the mean and median are equal, we have a perfectly symmetrical distribution. However, in cases where you have a leftward skew or a negative skewed distribution, the mean is going to be smaller than the median because, again, there's some really extremely small values over on the left side that are pulling that mean away from the median. So what are the best measures of central tendency by variable type? Well, for nominal level data, the best measure is the mode. For ordinal level data, the best measure is the median. For interval or ratio level data that is not skewed, the best measure of central tendency is the mean. However, when there is a skew and extremely large values or extremely small values can impact the mean, the median becomes the best measure of central tendency. Let's look at a few different ways of calculating the mean. So the mean we just discussed in the previous section is called the arithmetic mean. There's two more types of means that we will do in this lecture. The first is the weighted mean, and the second is the geometric mean. So the weighted mean is a set of numbers x1, x2 to xn with corresponding weights w1, w2 all the way to wn, and it's computed with the following formula where x bar over w, weighted mean, is equal to the weight of each value times the value plus the weight of the second value over times that value all over all the weights of our values. This is the same as saying if you had, let's say, repeating values like 1, 1, 1, 1, 2, 2, 2, then you had 4 3s, you could find the mean just adding everything up and dividing by the total number of observations, or you can say, well, 1 appears 3 times plus 2 appears 3 times, and then you can divide that whole thing by 6. So both ways are possible. Let's look at an application of the weighted mean. So one application of the weighted mean is to be able to calculate your final grade. So here I've posted basically our entire grade book and how I'm going to weight the course. So you'll see here the lecture quizzes are 5%, your homework is 10%, etc. Now let's make an assumption that a student, a random student, had these specific scores. They got 95% on their lecture quizzes, 90% on their homework, etc. Okay, you guys can have a look at the rest of those scores. The first thing we would do is we'd calculate the weighted score. And to do that, we take each ratio, so 5%, 0.05, right, 5% as a decimal, times 95% of it as a decimal, 0.95, and you repeat that across the board. And then you'd end up with a weighted score. So to get your final actual calculation here is you would add up your weighted score, and in this case that would reveal you got 0.84 or 84%, which means based on our syllabus you would have earned a B. And what's causing that grade to be lower than basically what it looks like with your lectures and homework? Well, it looks like that the student scored 75% on the final exam. The second type of mean is the geometric mean. So this is useful in finding the average change of percentages, ratios, indexes, or growth rates over time. It has wide application in business and economics because we are often interested in finding percentage changes in sales, salaries, or economic figures such as GDP. The geometric mean will always be less than or equal to the arithmetic mean, which is what we used in the previous section. How do we find the geometric mean? So the geometric mean can also be called GAR, or the geometric average rate. So here we're trying to find an average rate of growth. So here's the equation for the GAR. So the GAR is found by taking the nth root of 1 plus x1 times 1 plus x2, etc. Finally, you would subtract 1 from your product after you take the nth root and multiply by 100 to bring it back into a percentage. So here, x1, x2, and xn are the rates of change in each period represented as a decimal. Let's have a look at an example. So the return on investment earned by Atkins Construction for 4 successive years was 30%, 20%, minus 40%, and 200%. So we're going to go through the steps to be able to calculate the geometric rate of return. So here we have our percentage changes just taken from the question here. So first thing we're going to do is we're going to convert them into decimals by dividing each one by 100. And that means the first one becomes 0.3, the second 0.4, the third one, notice, is a negative, so it becomes negative 0.4, and the fourth one becomes 2. Now we add to 1. So we have, and now this became a rate of growth. So we have 1 plus 0.3, which is 1.3, 1 plus 0.2, which is 1.2. Here we have a negative, right, a reduction. So here we do 1 minus 0.04, 0.4, which is 0.6, and then finally 1 plus 2 is 3. Now let's plug it into the equation. So now let's take these values of 1.3, 1.2, etc. These are your 1 plus x's, so they would go into each of these parentheses. And in this case, we have 4 observations, so n equals 4. So here's our equation. We have the fourth root of 1.3 times 1.2 times 0.6 times 0.2. And once we find that value, we subtract 1 and multiply by 100. Here we have a result of 16.97%. This says the average annual rate of growth of this investment is 16.97%. There is one more geometric mean that we're going to look at. This is called the rate of increase over time. So you use this formula in the case where you have only the value at the end of the period and the value of the start of the period. So to use this formula, you won't be given percentages, you'll actually be given some kind of whole number. So in the example below, you're told about population in Las Vegas in 1990 and the population in Las Vegas in 2011. And what we want to know is what is the average annual increase in the population? Okay, so first thing we do is we want to figure out how many years have passed between those dates. And in this case, the number of years would be 2011 minus 1990, which is 21 years. So let's plug in our values. So the geometric mean equation becomes the 21st root of 584,539 over 258, 295. And from that, we'll subtract 1 once we calculate the root. So our result is 1.0397 minus 1, which is 0.0397. Let's convert that to percent, and we get the average rate of population growth in Nevada, or Las Vegas, Nevada, between 1990 and 2011 would be about 3.97% growth per year. This is the end of Lecture 3, Part 1. Please move on to Lecture 3, Part 2, where we will explore the variance standard deviation.